Hey everybody, Dr. A here, and in this video we're going to be exploring another example of a statically indeterminate beam. Now, given to us, we are being asked to compute the external support reactions, and we're told that the flexural rigidity is constant. So this beam is a little bit different than the ones we've seen in the previous couple of videos on this topic. This is a two-span continuous beam, okay? So it's still one member, N equals 1, but that one member is spanning two gaps, you could call them. One span is between points A and B, and the other span is from B to C. Each span is 3 meters long, and the applied load is a uniformly distributed load of 5 kilonewtons per meter. So at point A, we have a pin connection, and then at B and C, we have rollers. So let's go ahead and get started. We're going to write solution, and we're going to confirm by drawing the real beam that this is in fact statically indeterminate. So our real system, or our real beam, is going to look exactly like what's given to us, but we're going to draw it as a free body diagram. So here's AY and AX, and here is the applied load that we have of 5 kilonewtons per meter, and then we have a BY here and a CY here. And again, we want to draw those dimension lines as 3 meters and 3 meters. So clearly we see that we have 4 external support reactions. So R equals 4, and we have N equals 1. So the degree of indeterminacy is R minus 3N, which is 1 degree of indeterminacy, which means that we need one compatibility equation, and we need to select one of these external reactions to be the redundant, such that the primary system that we are about to draw is both statically determinate and stable. So I'm going to say let's select BY as the redundant. Now the reason why I'm going to choose BY as my redundant is because there are readily available deflection equations for simply supported beams with uniform loads. So this is one of the things you need to think about if you are given a choice to select something as a redundant. Select a redundant such that your deflection calculations will be convenient and not very tedious, okay? So I'm going to say let's select BY as the redundant, since this will create a statically determinate, stable primary system with convenient, let's call it conveniently calculatable deflections. Okay, a lot of silly words in there. Conveniently calculatable deflections. So let's go ahead and draw that primary system. Okay, so remember, in the primary system, it's going to look similar to the real system, except we are going to remove the effect of the redundant that we chose. We're going to completely remove it. So we're just going to have an AY and an AX. And we've got the uniform load here of 5 kilonewtons per meter. And we have CY here. And the entire span length is, of course, 6 meters. So this thing is going to deflect very symmetrically, even though that diagram doesn't look very symmetric, but it will be a symmetric deflection diagram. And right at the middle, at the 3 meter mark, we're going to have, of course, delta B, okay? Now, how do we calculate delta B? Well, that's where we are going to use some pre-derived formulas, or a pre-derived formula. So from most mechanics of materials or structural analysis textbooks, you can find a convenient formula for delta B for this particular load case as 5 WL to the fourth over 384 EI. So substituting values in, we're going to have 5 times 5 kilonewtons per meter times 6 meters to the fourth power over 384 EI. And that's going to give us 84.38 kilonewton meters cubed over EI. And that, of course, is deflecting downwards based on our diagram. So that's delta B. Now we're going to follow a similar procedure that we have seen in our other videos on this topic. We're going to now draw the redundant, I'm going to call this redund system. Now on the redundant system, we are going to geometrically draw the same kind of beam that we see in the primary system, except we're not going to have the real loads on it. We are going to have the redundant force acting on it like it's a real load. So there's going to be a little By that we apply to the middle, that's at 3 meters. And we're going to see that this thing is going to deflect kind of like this. It's supposed to be symmetrical, but this is my freehand, so it doesn't look very beautiful all the time. So that's going to be delta prime BB, and of course that's at the 3 meter and the 3 meter dimension line right there. So how do we calculate delta prime BB? Well, again, we're going to use a pre-derived formula, delta prime BB. And the pre-derived formula we're going to use is PL cubed over 48 EI. Again, that is the deflection at the midspan of a simply supported beam due to a single point load at its midspan. And you can find this formula in pretty much any mechanics of materials or structural analysis textbook. So P in this case is BY. That's going to be BY times 6 meters cubed over 48 EI. And substituting those values in, you should get 4.5 meters cubed times By all over E times I. And that's going to be an upward deflection because we have assumed By is pointing up here. Now we're going to set up our compatibility equation. And that is going to take the form of negative delta B plus delta prime BB equals 0. Then that's going to take that form when we say deflections pointing upward are positive. So we can substitute our two expressions for delta B and delta prime BB into this compatibility equation. And that's going to look like this, 84.38 kilonewton meters cubed with a negative in front of it over EI plus 4.5 meters cubed By over EI, all equals 0. And we can solve for By here, and we'll get a positive 18.75 kilonewtons reacting up. So that is one of our unknown support reactions, but the problem said solve for all of the external support reactions. So now we're going to apply equilibrium equations to solve for the remaining support reactions on the real beam. So I'm going to re-sketch the real beam here for us just for our reference so I don't have to continue to scroll up and down. And so the real beam has an AY, has an AX. On the opposite side, it has a CY. And then right in the middle, it has BY, which we know now. That's the 18.75 kilonewtons. And we can draw these dimension lines here as 3 meters and 3 meters. And we have the applied uniformly distributed load here as 5 kilonewtons per meter. So if you look here, we just have 3 external reactions left to solve for. Clearly, we can say sum of the forces in the x direction equals 0 and AX will be 0. We can then say sum of the moments about point A equals 0, taking counterclockwise rotations as positive. So that's going to be 18.75 kilonewtons times 3 meters. And then we're going to say plus CY times 6 meters minus 5 kilonewtons per meter times 6 meters times 3 meters all equals 0. So Cy comes out to be 5.625 kilonewtons reacting upwards. Then we're going to say sum of the forces in the y direction equals 0, taking forces pointing up as positive. And so looking at our real beam free body diagram, we're going to have Ay minus 5 kilonewtons per meter times 6 meters plus 18.75 kilonewtons. That was our By that we calculated from our compatibility equation, plus the Cy we just solved for, 5.625 kilonewtons equals 0. Doing some rearranging, we can solve for Ay, and that also equals 5.625 kilonewtons pointing up. And that makes sense that Ay and Cy are equal because the real beam is a symmetrically loaded two-span continuous beam. So it makes sense that Ay and Cy should be the same number. So that concludes this example. If we wanted to go a step further and draw the shear and moment diagrams for this beam, we could. But the problem didn't ask for that. It just asked for all the externals, and that's what we did. So if you found this video helpful, please hit like and subscribe. Thanks for watching.